Okay, today we will discuss the experimental proof that there are energy levels in an atom. Already we have discussed that in an atom there is a central part which is called as nucleus, and electrons are revolving around the nucleus in different specific orbits. We call them shells: K shell, L shell, M shell, N shell, and so on. Now, energy in each shell is having a particular value which we have already calculated. Now, what is the experimental proof that there are energy levels in an atom? For that, in 1914, James Franck and Franck-Hartz performed an experiment which demonstrated the existence of excited states in mercury atom, helping to confirm the quantum theory which predicted that electron occupied only discrete quantized energy states. Now, question is how to excite an electron from one level to another level. For example, if this is K shell and I want to excite the electron to L shell, what I can do? There are different methods. One method is that we throw frequency of a particular value which correspond to the energy difference between this shell and this shell. So electron will absorb this photon and it will take electron from this level to this level. This is excitation of electron by photon, because I am using here a photon. Another method can be that the same electron I am taking and I am accelerating another electron. When the energy of this electron becomes equal to the difference in energy between these two shells. So this electron will knock out this electron will excite this electron from here to here, and it will be scattered in a different direction. So energy of the electron is absorbed here. If this electron has got lesser energy than this difference of energy, then electron absorption will not take place. Rather, electron will go straight through the material. So these are two different methods by which we can excite an electron in an atom. Here in this experiment, we will use this second method. Electrons were accelerated by a voltage towards a positively charged grid in a glass envelope filled with mercury vapors. When I use the term vapor, I mean it is in the gaseous state. The mercury is in the gaseous state so that one atom is not influencing the other atom. Every atom is independent. Now, this is the selection for that. You can see this is an experiment in which electrons are produced by electron gun here. Electrons are accelerated towards the grid which is positively charged. Electron itself being negatively charged, it will be exerted a force which will accelerate the electron toward the positive grid. I will keep on increasing the potential difference between them. And when I increase the potential difference, you can see here, this is the accelerating voltage. When it reaches to a particular value, then suddenly, and this is what? This is the collection of electron or current. Current is measured by this ammeter. Now, initially, the current increases. When it reaches to a particular value, then it will suddenly reduce. Current will start reducing to a minimum value. And then again, electron will be started, because this electron is lost energy, so it will come to the minimum value of energy. And then if I further increase the potential again, the electron will be accelerated. It will go to the maximum value. Again, it will reduce to the minimum, again to the maximum, and so on. So you see here peaks. One peak, another peak, another peak. Now these peaks correspond to the potential energy of the electron, which is taken from the lower energy level to the higher energy level. So this is what the Franck-Hartz did. Past the grid was a collection plate held at a small negative voltage with respect to the grid. Value of the accelerating voltage, where the current dropped, gave a measure of the energy necessary to force an electron to an excited state. It means electron will go from the ground state to the excited state when this particular value of potential is achieved. Potential means accelerating potential. Then electrons are accelerated in the Franck-Hartz apparatus, and collecting current rises with accelerated voltage. It means more and more electrons will reach to the grid. As the Franck-Hartz data shows, when accelerating voltage reaches 4.9 volts, the current sharply drops. The current sharply drops, indicating the sharp onset of a new phenomena which takes enough energy away from the electron that they cannot reach the collector. Now this is what it is. Electrons are being accelerated. Their energy will increase. When it reaches to energy corresponding to 4.9 electron volt, then the atom will absorb the energy by exciting the electron to the higher state, and these incident electrons will lose energy because they are used up in increasing the energy of the electron. Again, those slow electrons now which are slowed down by the excitation of the atom, those slow electrons will again start increasing the energy, and at another voltage again you will see that there will be a sharp increase and then start decreasing. This is what it is. Drop is attributed to the inelastic collision between the accelerated electrons and atomic electron in the mercury atom. Why inelastic? Because the incident electron loses energy by exciting the electron of the atom to the higher energy state. The sudden onset suggests that the mercury electron cannot accept any energy until it reaches the threshold for elevating them to an excited state. So you can see here the electrons are not getting, atomic electrons I mean, are not getting any energy until their energy becomes equal to this, or this becomes equal to this. This is the accelerating voltage V, and if we multiplied V with the charge of the electron, this will give me the kinetic energy and potential energy. This 4.9 volt excited state corresponds to a strong line in the ultraviolet emission spectrum of mercury at 254 nanometer. If you convert this 254 nanometer wavelength into energy, by this relation, E is equal to H into C divided by lambda. H is the Planck's constant, C is the speed of light, and lambda is this value, which is 254 nanometer. If you substitute all these values here, you will get a value which will be equal to 4.9 electron volt. It will come in joules, and you can convert it into electron volts, so it will be 4.9 electron volts. Drop in the collected current occurs at multiplets of 4.9 volts. Multiplets mean 4.9 multiplied by 2. So this will come out to be 9.8. You can see that again at 9.8 here, this one, this is 9.8, this is 10, and this is less than that 10, 9.8. Again, there is a sharp peak, again reduce in current, and then 3 multiplied by 4.9, this will come here. This will be equal to 12 or 13 point something. So all this shows that electron can absorb energy only when incident electron has got a specific value of energy. Drop in the collected current occurs at multiples of 4.9 volt, since an accelerated electron which has lost 4.9 electron volt of energy removed in a collision can be reaccelerated to produce other such collisions of multiples of 4.9. So you can write 4.9 first excitation, again 4.9 multiplied by 2, second excitation, second peak, and 4.9 multiplied by 3, this will give you the third peak. So this is the experimental setup. Mercury is enclosed here in this container. This is a glass tube. Mercury is always at low pressure. Why low pressure? Because if atoms are very close to each other, mercury is at high pressure, one atom will influence the other atom. So for that purpose, we have to move the atoms away from each other, and that's possible when I am keeping the pressure in the tube at low value. Now you see this is negative and this is negative, but here is a big negative and here is a small negative. Why it is so? Because here I give a big potential, negative potential. Compared to that, I give a small negative potential because I want to collect electron here. If this is the positive, if I leave it like this, electron will not reach here. For example, if I say apply a potential difference of 50 volt here in this case, so this will be at negative 50 and this will be at positive 45. So there will be, and this will be also at positive, this is negative 50, this is positive 50, and then this will be negative 45. So 45 और 50 के दरम्यान में जो gap है, that will be the reason that electron will reach to the collecting plate. This is called as collecting plate. Franck-Hartz data for the mercury is this original Franck-Hartz data shows electron losing 4.9 electron volt per collision with mercury atoms. It is possible to observe 10 sequential bumps at interval of 4.9 volts. You can see 1, 2, 3, 4, 5, 6, 7, 8, and 9. Franck-Hartz display for mercury shown at the left was formed by sweeping the accelerating voltage and recording current versus voltage on an oscilloscope in XY mode. The measured separation of the peaks correspond to the excitation of energy of involved mercury transition. What does it mean? If this is your high energy, this is your low energy, then this difference in energy will be equal to 4.9 electron volt. Okay, so emission of the extra energy will also take place in this case. So this is the corresponding value on an oscilloscope. You can see it here, different peaks are given here. Similarly, I can perform this experiment for neon gas. The process of absorption of energy from accelerating collisions produce visible evidence. When accelerated electron excite the electron in neon to upper state, they de-excite in such a way as to produce a visible glow in the gas region in which the excitation is taking place. You might have seen neon display tubes. So this is working on this basis. There are about 10 excited level in the range of 18.3 to 19.5 electron volt. They de-excite by dropping lower states at 16.57 and 16.79 electron volt. This energy difference gives light in visible range. You know when I say light in the visible range, I mean the colors of the light will be between red and violet. Okay, and color mean the frequency. So I will say that lowest value of the energy will be for the red color, and the highest value of the energy will be for the violet color. The accelerating voltage from Franck-Hartz tube used to produce the picture was capable of producing an accelerating voltage about 80 volts. So we could get up to 4 collisions. This can be seen under proper condition as 4 bands of light from the de-excitation in the region. Emission takes place when I say electron is taking energy in going from here to here. When it comes back, this energy is higher and this energy is lower, EF and I will say EI. EF is greater than EI. So difference in energy, EF minus EI, will be emitted in the form of photon H into nu 1, for example. So this will be particular frequency.